tomorrow I will send you the email with a follow-up, so you will get all information and the presentation. In case you want to refresh some knowledges, you can always find it in your email. Okay, thank you for joining us today. I hope this information is going to be useful for you. And while others are joining in, let's talk Intellias a bit. Interesting projects, international clients, global representation, 7 development centers, and more than 500 open positions. That's what Intellias is about. We create unique software solutions for more than 2 billion people with the help of 2,000 experienced specialists on the board. And no matter how fast we grow, we always adhere to the people-first approach. That's why Intellias is recognized as the best employer according to Dow, Forbes, and other top ratings. So I invite you to check our website with the open positions, and who knows, maybe a career match will happen. Now, just a couple of technical issues. Please hold your microphones muted during the presentations. You can write your questions to the chat and Vasyl will answer them on the way or after during the Q&A session. And that's it. Let's get started. I would like to introduce our speaker, Vasyl Bilous, C++ engineer lead at Intellias. Vasyl, glad you're here and the word is yours.
Yep. Hi, everyone. Hear me well?
Yeah.
Yeah.
Okay, cool. So yeah, let's start then. So my name is Vasyl. I will be talking today about performance. So this talk will be about measuring your performance, knowing your performance, some typical ways of giving a hint of your performance. And I will not be focusing on the ways on how to improve it or what can be the common pitfalls here. So this is only a rough introduction into this topic, and the ideas on how to improve it and yeah, closer to the code are, yeah, that's another big topic and not only for one talk. So yeah, a bit about me. I'm a C++ engineer with more than 10 years of experience. My experience includes working on electronic design automation solution and also working on different kind of navigation solutions for automotive customers. I generally enjoy working with C++. I'm looking forward to standard library growth because yeah, C++ language is already big enough, but we are lacking a big and huge library with all the stuff there. And aside from that, I enjoy traveling, I enjoy hiking, driving by car, spending time in nature, and yeah, being a real human. So about this talk, I will start first with a rough idea what is profiling and why should you care. Then I will show you typical profiler types and give idea how they work. And then I will walk you through some maybe handwritten approach and typical and existing solutions in the field. And yeah, with some bonus slide for watchdog technique. And then I will wrap up and describe what solution can be applied in which conditions and what's, yeah, where it fits the best. So yeah, let's go forward. So profiling, there is a definition from Wikipedia that's a form of dynamic program analysis, which is focused on collecting the time and resources spent when the program is run. So dynamic analysis means this is collected when the program is run. That's not about reading or analyzing the code statically. Yeah, you will not have the performance data if you will not run the program. And usually this is achieved by adding some additional logic to execute, which will then give you an idea of what is executed at the given amount of at the given moment of time and how long does it take. And for C++, yeah, the language is known to be used where the resources and the time matters, because this is the language where you don't pay for what you don't use. And that usually means that you are interested in how the program runs and what is the performance of your program, because yeah, this is about efficiency and the time. And the profiling here is actually a key to success, because you have to know what to address. what is running slower in your program and what is taking more resources. And there is a known Pareto rule which states that roughly 80% of consequences come from 20% of the causes. And when applied to performance, it usually means that only 20% of code actually spends 80% of time when it is being run. And even more than that, it's often the case that only 10% of code takes 90% amount of time when it is being executed. And when it comes to profiling, this is actually a tool which gives an insight what are those 10% of code and where you should pay attention. So going next, I will shortly describe the typical profiler types and how do they work. So first one is a sampling one. This one is based on probing the current instruction of the program which is being executed, and that's being done by interrupting the program on some regular intervals of time and recording the data about the current state and the current function call, or maybe the current function line if that information is available. This technique is usually has minimal impact on the program, so it doesn't slow down the program considerably, but it also has low precision when compared to the others, because it is limited to the frequency of this sampling. And it is often the case that when you are interested in some particular function or some particular code block, you will not see the time distribution per each line of code or per each instruction, because its time to execute might be lower than this sampling interval, and it will simply not appear in the result. But still, this will give you an idea of what are the main function calls that take the most time and what they call graph, and where the time goes for. An example of these tools include Microsoft Visual Studio Profiler, which is built in the Visual Studio and comes for free with it. That's also an Intel vTune solution. It offers the sampling approach, but it also offers it also works combined with some Intel specific processor instructions, and that might give you more insight on processor behavior, on branch prediction, on cache state, and so on. Also, there is a known perf tool for Linux, and that's based on also the kernel logic, but that's all about it at the moment. Second kind of profilers are the instrumentation ones. Those are intrusive to the code and they are based on adding some instructions to execute. That might be some explicit, like you have to adjust and modify your code to add them, or that might be done in some automatic way, maybe on link time, but still this affects the resulting program. And of course, this might affect the resulting performance of the program. And if that effect is big enough, that might cause some side effects. For example, in multi-threaded environment, the execution timing might shift from the timing when it is run without instrumentation, and that might lead to some unexpected bugs or issues alike. But this technique is usually very precise, and when you need precision and when you know where you focus on, then you can use this technique. It can be manual when you place the instrumentation code lines by hand. It can be automatic. For example, the tool can automatically add the profiler instructions for each function call and for each function returns. And it can be assisted when, for example, the tool first, for example, when the program is first run with sampling profiler, then there will be an idea what the hotspot, what are the functions which take the most, and then only for that, for example, hot path, the instrumentation can be added to not include it everywhere in the program and to not cause the general slowdown. And an example of that is some handcrafted implementation, which I remember I did and I saw in various places, and I will show you next some very simple typical approach for that. And existing tools include Easy Profiler, that's also Tracy Profiler, and also Microsoft Visual Studio has the instrumentation mode available for this as well. And the third kind of this tool is simulation ones. For these tools, the program is run unmodified, but it is run as if it is run on virtual machine or on virtual CPU. And such kind of tools usually translate the instructions to some another set, to some custom set. Then for that set, the tool adds its specific instructions or some code to execute. It essentially grabs them. Then this translation goes in backwards order, and only then that modified instruction set is getting executed on real CPU. This technique is very powerful because that will give you breakdown per each instruction, and that also can give you breakdown not only per like the timing of the program run, but also for any other resource. For example, for memory, this can track down and record every memory access, every allocation and delete and access, and that will give you an option to track down memory issues, memory access issues. That can also help you with threading issues, with using threads, locks, and everything like that. And yeah, and there are also tools available for this. For example, to analyze the cache and branch prediction. But this comes at a huge cost. So example of this tool is Valgrind. This is maybe the most known one. It includes actually a set of different tools, one of which is CallGrind, which is for collecting the call stack graph with timings, but also Valgrind, it's actually a suite of tools, and it includes also mem check for the memory issues, and there are also a number of the tools available. But yeah, remember that comes at a huge cost, and also the Valgrind has limitations on what actually the program can do, and it can cause dramatic changes in the flow and the code path which is executed for the program, and it can differ differ very much from the normal program execution. Yep, having this said, going to next slide, and this one is about instrumentation technique, and this is like a simple approach, handwritten approach to manually instrument the code. The way might look like RAII one. So this is done via class, which is acting as a block. It has no methods, only constructor and destructor, and essentially in the constructor it records the timestamp and the name of the block which is currently opened, and when it is being destructed, for example, when the execution leaves the function or the scope, then it records the timestamp of this destructor call, and then there should be some central place, some aggregator of this, which will then record this difference in timings, and that will be actually duration of this call, and that can be then dumped in some way and analyzed later. So I will then now switch to some code, because yeah, this is what I have prepared already. So the implementation can look like this. First, let me know if you see my screen with Visual Studio.
Yes, we see.
Okay, cool. So the simple and naive approach might look like this. It's a simple class with no methods except the constructor and destructor. And the data is stored as an optional field. And it might include the block name, which is a custom name specified in the code, or it might be the auto-generated function name. And it also includes the timestamp when this block has started, and then when when the destructor was called. And then let me go back. Someone is talking.
Часом немає чогось без м'яса? Раптом.
Okay. Yeah, I have no way to mute. Let me try to do.
Я бачу руку, як мінімум, я вже не помру від голоду. Ну тоді все окей, все окей. Тут хтось сидить?
Okay, I will
Я з вами посижу.
Алло. 25.
Okay, let's proceed for a while. So yeah, and the usage of this code block. Someone else is talking, or okay, weird things happen. So first of all, yeah, the implementation, sorry, I clicked the wrong button. Yeah, I have to share now. Yeah, so implementation might look like this. So there is a singleton profiler instance, and in the constructor, it creates this structure, which is which includes the name of the block and also the timestamp when this was called. And in the destructor of this scope block, it just passes this block to the profiler back. And the profiler then should collect this data and process it later, maybe to dump to some way. And the usage of this can be seen here. So the explicit use might look like this. So you simply instantiate the block with some custom name, some meaningful name for you, of course, and that can be done per scope. And yeah, that's the job is done actually here, because for any code path execution, whether the function returns early or not, this will get recorded anyway, or maybe there will be exception. This will get recorded anyway. And also it might be done in a bit convenient way. So the macro can be defined to actually decrease the typing work. And it might look like just defining the variable name with line number name, appending as a suffix name. And yeah, that's it. And also for convenience for functions, yeah, it can be done without arguments, because a compiler already knows the name of the function it currently executes, and we can make use of it. When, for example, for the function, we are not interested to go into details, and we are not interested into knowing what the part of the function exactly takes which time. And for this example, I have implemented it in a way that the profiler starts at the beginning of the program, and everything it has collected is going to be dumped into human readable JSON file. Yeah, there is, I can show the implementation here actually. So yeah, this profiler instance can be implemented as simple singleton. And when you start the block, it just creates the structure and records the timestamp of now. And of course, with invalid time point, because we don't know when this will finish. And yeah, it already pushes, it already stores the block, because we already want to record it because it is already started. And the whole processing is done in a separate thread, so that the execution path of the program will not get a performance hit. performance penalty by these operations of this profiler instance. And then when the block ends, it does essentially the same, just it fills the stop time point so that it can be then calculated how much time does it take. And in a separate thread, there is a simple loop which waits for new data to come. And once it appears, it just goes through the available blocks and simply dumps them into JSON structure. Here I have used the RapidJSON library because that's open source one and very simple to use, and it doesn't require to construct the whole JSON model, and you can just output it as you by the way you have the data. And when I run the program, I have implemented some loops with some simple waitings in those loops. The execution is done, and here's the result. It's a simple JSON file, and which looks like a JSON tree, and which has for every name, for every node, it has the duration. And of course, it can have nested ones, and that will give an idea about the actually call graph. And there are multiple ones because that was executed in a loop, but in the end, this will finish. Okay, back to the presentation. Oh no, that's not what I wanted to do. Let me scroll this. Okay. So this is a very easy technique, very simple technique, which doesn't require any tool, but it of course relies on you on how to implement this. And the usual approach here is only to instrument with this on the only areas where you are interested in the performance, where you know that something might take too long. And then it can be dumped into any representation. It can be JSON, it can be some binary format, whatever, and then it can be used to be loaded into some tool to actually make this very user-friendly, good-looking, and then someone can analyze this. And of course, this technique is not really something I have invented. And there are also existing implementations available for this. One of them is Easy Profiler. And this is an open source, lightweight, and cross-platform tool, which essentially implements that approach. And it also usually works with adding some macro lines into your code. And those macros expand to something like those blocks I have shown you, and it can be configurable at compile time. For example, if you are not interested into collecting these profiling statistics, you can just not define the macro for profiling, and then the resulting code will not have anything related to profiling because the macro will expand to nothing. But you can opt in with define, and then the code will be in place. And when the program is run with this profiling enabled, the collecting of the data will start, and then it will be available for examining. This tool has support for dumping into the file directly. It has some binary format, but also you can connect to the running program live via network by specifying the IP address and the port number, and the data will stream live, and you can use this to actually profile the program at the needed amount of time when you actually are doing something of interest, when you are triggering the logic or the flow of the program, which can take too much time or it can have potential problem. This tool also offers possibility to record some attributes like integers, like strings, like arrays, and that can be useful to, for example, record the function arguments, or maybe internal state of the algorithm which is executing at the moment. And that will give more idea of what the program state was and what was it doing and why. Also, it offers blocks colorization, so that it can be used to distinguish different types of blocks. For example, it can be used to distinguish normal function calls, and then it can be used to distinguish it from the amount of time when some lock was held, and that can help to analyze the performance issues related to locking when there is lock contention, and that will give more idea of the program state. For this, I think I also have the example implemented, like the very same code, but only using the Easy Profiler, just to show you the example approach. Yeah, the code is very same. There are some functions doing some work, actually sleeping, and they are used in some loop. And the use of this is just to insert these macros with some custom names. And you can also keep track of additional values. For example, here I just append the loop index in it, or it can be used just to track the function by passing this easy function macro. And I think that's it. And for this approach, I have done it to dump the data to the file, which then can be used like by opening the tool. This is how it looks like. So I have it recently done, and yeah, it looks like this. So then you can check the block. It will show you the time spent, and also it will show you the nice statistics of this function. For example, what's the number of calls of this session, of this function, and what's the time distribution, what's the average time of this call, minimum, maximum, and also what's the percentage of the whole time this of the program execution that was spent in here in this block. So yeah, very simple tool, but also very powerful, and it is used not only in some examples like here, but also in real production code and in large projects. Yeah, coming back to the presentation. Yeah, let me do this again. No, it doesn't offer me this. I have to scroll this. Okay, so another kind of tool is Tracer Profiler. This is also an open source tool. It is also cross-platform one. It is real-time only, so it doesn't seem to offer the way to just run the instrumented application and dump all the data to the file. This relies only on the fact that you connect to your application, which is already running via network, and then you will see the data gathered. But the benefit of this is that the overhead of running the application with profiling collection statistics is even less compared to the approach for Easy Profiler. This tool is under active development. Its version is not even reached one, and this is a recent one. And yeah, it also has support for GPU profiling. So it also has a focus on 3D rendering, profiling, frame profiling, and so on. And it is receiving some recent fixes and features. It has decent documentation. It has also attractive UI, which I found much more good looking compared to the Easy Profiler. But the general approach is here, yeah, I would say the same as in previous one. Another kind of tool is Valgrind. This is what I mentioned before as simulation one. This is, yeah, as I mentioned, this is essentially when the program is run under this tool, it is run as if under virtual machine, because it involves translating the program instructions into some intermediate representation for Valgrind. which then is modified by inserting some custom instructions to perform some metrics. For call grind, for example, this will result in appending some records for current function call, current instruction, and so on. And yeah, then it is being translated back, and then it is being run on real CPU. This tool is Linux only. It highly depends on the operating system and on the kernel details. And yeah, it's at the moment the note is that it will simply not appear for Windows, for example. Yeah, actually, as I mentioned, the Valgrind is actually a set of tools. There is also memcheck, there's Hellgrind, Massive, and others. Callgrind is only one of them, which is focused on the performance. The good thing is here that you don't have to modify your program to be run. There is no instrumentation, like manual instrumentation required for it. But and also the good thing is that it will profile all the external libraries, all the external function calls from your program, and it will show them if the symbols are present. But the performance hit is really fatal because the program slowdown is, from what I've seen, from 20 times up to 100. And yeah, that means that this tool is simply not usable for many of the approaches. And also, due to the nature of this execution, it means that this the code which is then run on real CPU, it is run sequentially. So all the multi-threaded execution that the program might have, it ends up essentially being sequentialized, because yeah, Valgrind has no support for running that in parallel, and that would be too hard for it. And that, of course, will slow down your program even more. And if the program relies on the multi-threading, then Valgrind might be not an option at all. Yeah, I'm going to next one. Of course, the Visual Studio offered this profiler, starting from some versions. And the profiler can be run in sampling mode, and it can also be run in instrumentation mode. And the screenshot here is actually taken for sampling mode for the first example that I showed you. And this is the code block for the JSON dump. And as you can see here, the metric is only available only for some lines. So there are more than 10 lines of code doing something, but only 2 of them actually have some sampling statistic available. And that's due to the nature of the sampling profiling, because it is done by interrupting your program with some periods of time. And it, of course, depends where the program execution is at that time and how much instructions it has already executed when it was run. And that will end up in the precision being low when you need to analyze performance like tied to each line of code. But still, this is a very good option when you need an insight on the general program performance and what are the parts of the program where the execution time is spent the most. And this is a good start because you can do it like in parallel with your feature development or bug fixing. You can do the code change and then test it for performance right away to see how it performs and whether you can do, whether there's a serious issue right away, and you can just avoid like going into some common pitfalls of introducing some performance regressions. But yeah, it is also only for Windows. Yeah, that's obvious. That's obvious downside of it. Yep. And then I will try to go next. So having that said, for previous approaches, I want to also mention the approach of collecting the statistics, which are also known as flat profiler statistics. They mean that you will not have the call graph, you will not have the graph of all function calls, that your program was executing, but you can paste this manual instrumentation to gather the flat statistics of how often some function is called and what's the average time of execution and what's the minimum and maximum time of execution of that function or code block. The usual approach, I will jump back to the code, is I would say almost the same as for the manual instrumentation as I have shown you on the first time. Let me do this. So yeah, this implementation, yeah, again looks like this. It's a very simple class that records the start timestamp on construction and also records the time when it was destructed, and then yeah, like here, and then there is some agent, I called it here metric agent, that can aggregate, that can store these statistics. Let me scroll up. Okay, yeah, here it can store it into some container, and the actual processing and recording can happen in parallel thread, and that can happen not on each event occurrence, but it can happen on with very big after some period of times. For example, it can happen each 5-10 minutes, each half an hour, depending on yeah, how long does the program usually run. And yeah, and the implementation might look like this. So the separate thread will wait for new records to be available, and if the dump interval, the timeout has not yet reached, then it will just continue to wait again. But if the timeout, the interval has already passed, then it will proceed below, and then it will calculate for each name of the event, it will calculate the minimum, maximum time. It will also calculate the mean time, which essentially is the sum of all times divided by number of them. And then it can be simply, in this case, put into console, and that's it. And again, for this example, the example code looks similar. There are some function calls which are just sleeping. Imagine they are doing some very clever work, and they are called in the loop. And yeah, when I call this, there are some regular intervals of time. In this case, I have used 1 second, and for each of them, it can print aggregated statistics in a way like this. And yeah, from this you can know that, for example, inner loop for 1 second was called 12 times, and the mean time was 64 milliseconds, and the minimum and maximum was varying like this. Yeah, so this is the way. Yeah, let me proceed here. I have to learn how to use this. Yeah, and this approach can be used in production for all the time because it has very low overhead. Because for real code, it only needs to record the occurrence of this event and just store it somewhere in the array or in some container in some way. And that's usually a very fast operation. And the processing also can happen in a separate thread, and it can happen at large intervals of time, so that the program execution will not notice this. And when the program is run on some real hardware with some real set of data, maybe with end user and with some end user use cases, then these statistics will be available if, for example, in the application logs. And if there is some problem with performance, for example, there is when the user does something with a feature and then it takes very long in such conditions, then these logs can be analyzed by engineer, and engineer can conclude whether what exactly there was executing slow, and then conclude what can go wrong. For example, the issue might be that the some logic was executed too often, or there was some unexpected spike in the time of execution of something, and that will give an idea where the focus of the attention should be. Yeah, that's it for these statistics. I see there are some questions already in the chat. I will come back to the questions later at the end, because yeah, I don't have, yeah, it's not really convenient for me to switch to them right now. And yeah, oh sorry. And as a bonus here, I want to talk about watchdog technique. It's also a bit similar to the technique about metrics and manual instrumentation, but this has a bit different use case. This allows you to be aware of cases when something is being executed way too long. For example, there is some function or some code block or some task which should take usually to execute maybe 1 second, and you don't expect it to be executed more than 5 seconds. And it will be an issue actually if it will be executed so long, because it might be executed in some loop or in some thread pool, or it can be like a task on which something else depends on. And if the time of the execution will spend too long, then everything else will not get executed and the program will essentially stall. And for user experience, this will look like the program does nothing, or something is not updated, or it is just not responsible, and so on. This is usually implemented as a timer, or it looks like a timer. And yeah, the simplest approach that I have also implemented might look like this one. Let me show it. Yeah, so yeah, this is maybe the simplest and naive approach. The watchdog class, which receives the timeout value and the function to call if the timeout actually is reached. And what does it essentially do? It starts this threading constructor, and that thread is stopped in the destructor, and this thread is just waiting for the timeout, or it is waiting for notification. And if the notification is coming before the timeout, then it means the watchdog was stopped in time, so timeout was not exceeded, and that's fine. But if the notification was not received, then it means the timeout has expired. So for example, the timeout was 2 seconds, there was no notification, then this should be false, and that means this has to trigger the callback and notify the user of this watchdog that something was executing too long. For this example, yeah, I have the example, my usage might look like this. So for example, for the function, I do not expect it to execute longer than 1 second. And if it does, I just print the message to the console about that. And also here in the loop, I do the same with some handcrafted log messages. And here actually I expect it to happen because this one is executing for 30 milliseconds, but it is executed 50 times. So that will be already 1.5 seconds. And also there is something else being executed. So that's for sure more than 1 second. And that should lead to expiry. And the outer loop also, or I mean, not the outer loop, but the whole code block, this also takes more than 2 seconds because that's repeated 5 times. So we should be able to see this in the log. And the main point is that these log messages should occur concurrently. So because that's being done from other thread, it means that it will be shown and the notification will come as soon as possible. It will not come when, for example, this code block or this code block reaches the end here, reaches the end of scope. which might not be even the case if something is took forever. So, and when run this program, yeah, after one iteration, I can see the outer loop times out, and then when 2 seconds is spent, I can see that everything times out. And that log message comes at different times. That shows that this approach is actually concurrent and that's been working asynchronously. Yeah, back to the presentation. Yeah, I have to scroll it again. I have to remember the keyboard shortcut for this. Yeah, so that was an example implementation. It might be not very efficient because it starts the new thread in constructor, and that's actually pretty heavy resource, and that might be somehow optimized. But the general approach is like this, and the power of this technique is actually to give the feedback of some long execution as soon as possible. And also this can be used to track the executions that never end. For example, there is some code block that will acquire mutex, and there is also some parallel thread that will also acquire some mutexes and will also try to acquire that mutex, and there can be deadlock actually. And with this technique, you can actually be aware of this. There can be a notification implemented to track this. And one of the ways to handle this is to make the program restart. And that's very useful for deadlock case, because there is no healing. You can do nothing with the program because the thread is stuck forever. And watchdog technique is usually used to like a hard reset, because there is no other reset possible, and it can be used to restart the program from scratch, but also with maybe some login, or maybe if that's a crash, the call stack can be recorded, which shows the call stack pointing to the task that was executed, and that might give an idea what exactly was stuck on what mutex, and then yeah, the developer will have much more information than the log line. And to summarize this, with this different technique, I want to mention the general idea on what approach can be used at what time. So for sampling profiler, this one is good enough when you just need to have the general time distribution for a program. For example, when you are not interested into time distribution per each line of code, you only need to gather the overview of the program execution and the profiling statistics. For example, you want to nail down the program part, some component which takes the most time, where the processing is, where the time comes from the most. And then that can be used to actually plan some actions to maybe deep dive there, to maybe plan some improvements or think about that and so on. And yeah, that's easy also because it requires no changes in the code, and that's really easy to use, and yeah, good solution for a starting point. The instrumentation one requires some actions. It requires to at least recompile the program, but usually to modify the source code, and but that gives you full control of what you collect from the program, and that might also bring you possibility to record some additional data, some additional attributes for maybe some internal states for algorithm, and that might give also an idea what is executed when and why, and what can be an idea to improve this area. And this can be always on, or I mean always on, like always compiled in, and only configurable whether it is started at runtime. Because if you don't instrument your whole program, but only key areas of interest, then the performance hit will be really minimal, and it can be always on, and then it can be used to be run on real hardware which you can have no access to, or by real customer, by a real end user, and then from real run environment you have the performance statistics, and that will help you to improve the performance with in real environment. Simulation one approach is really deep and powerful. It's maybe the most detailed one, but it is also the most costly one. And I would use this one only when I'm sure I need it. When I figure out when such a granularity and such a performance hit that it will induce, I'm okay with it. So, but that's definitely not a way to follow for like a first step. And the watchdog, I think it can be used in parallel to those. It's not a replacement, but it is a technique to gather other kind of data to actually know when at which stage and when the program execution slows down or it gets stuck, and that's maybe a solution to be able to track some bugs already. And the key for this is to measure first. So you should not start working with performance, addressing some performance by just looking at code and considering this is maybe slow. That's wrong. So there is a quote from Donald Knuth that premature optimization is the root of all evil, because you will never guess what the problem with performance is, especially when the code base is large enough. And as I have mentioned in the beginning of the talk, due to Pareto principle, there might be only a very small amount of code which is actually consuming your time the most, and there can be hardly an idea where the code is. And spending time on the code which might be inefficient, but it is executed very rarely, and it still takes less time compared to other. That's just unneeded effort and might result in introducing some bugs, because optimization, when you want to optimize for speed, that might change the flow of the logic, and that of course can bring some bugs. So the general rule here is always measure first, and this is what the profiling is for, and the profiling tools of different kind can help you here. And having that said, I want to thank you. That's all that I have planned to share with you. This is only a rough overview of this area about profiling and tools and approaches. And having this said, I'm now open to the questions. Let me then, oh, sorry, no, not this one. I will stop sharing now because I have only one screen now, and I will go to chat, and then I will try to address the questions. So for library for JSON, I already replied, so that's rapid JSON. For Visual Studio for Mac, I actually am not aware because I have never used Mac. I'm lucky or not, but have never tried, so maybe someone else can answer this. Okay. Okay, there is button from current slide. Okay, thanks, I have missed that. What about memory fragmentation and its impact on performance? So this is more about potential root cause of the problems. To help nail down such problems, I think the right approach is to choose the proper tool. So when you know that the problem might be with fragmentation, with memory access, I think the tool you have to use is the one that allows you to collect these statistics. So I would imagine that the tool that will collect the hit and miss statistics for the data being accessed in memory, also maybe some branch and cache prediction, and then that will give you more insight on this. But that's already more deep than just timings for the function calls and code blocks, just for set of code being executed. And I would think that that tool needs to be used when you are sure that this is the code where it is spent a lot of time, and there is a problem, and maybe the bottleneck is here. It's in this small algorithm, and you need to make it more robust. And then you have to choose another tool, which will give you more information, and then you can address this. Yeah, hope this answers your question. You're welcome. Yeah, I'm glad that you enjoyed it. I hope you enjoyed it, because for me it was maybe the first time for such quite wide audience that I was sharing with, and yeah, I'm glad that at least some of you enjoyed this. So in case, if anyone else has question, you can just unmute and ask. Oh, okay, there is one question. What can we do to use Valgrind? How we should design our program to get used to Valgrind? Obviously, we maybe divide the program into modules if possible, or we can't do anything about it. For Valgrind, I think what I imagine I could do if I had to use Valgrind, I will then split it into parts and maybe run some isolated parts like components, maybe in some synthetic tests, or maybe like roughly say some unit test, or roughly like that. So it will not run at a full scale with all the logic. And in this mode, you can focus on the particular algorithm without maybe multi-threading, or maybe with minimal multi-threading. And then this tool will give you the full power. And the slowdown might be still very big, might be 10, 20, 30,000, 10, 20, 30 times. But since this is very located to the code, to the particular code, then it might be acceptable and you can wait. Because running the whole program with the whole solution, for example, I could imagine some navigation which runs into the real car, that will slow down so much that just not only it, but also nothing else can get executed on this device in the car. Then it's just unusable. So I would imagine that you just run it on the certain small portion of the program. Yeah. Okay. Still we have some time for questions if anyone has. You can just unmute, so because I see no questions in the chat, and raise your voice.
I guess we will just wait several more minutes. Maybe someone will come up with some new questions. And I want just to thank you for a great presentation. And thank you, audience. I hope it was useful for you guys. And just a short reminder that tomorrow I will send you the follow-up in case you want to refresh something, and you will always have a possibility to get it.
Cool. Will we have some possibility to maybe ask a question after the talk? Maybe so like a post question, or
I will send like a short survey, and people if you want, I can also share like your maybe LinkedIn or stuff, so people can DM you if you don't mind.
Okay. Yeah, cool. So I'm open to feedback because it was my first talk for such a wide audience, and of course I'm interested whether you liked it or not and what can be improved. But I hope that you enjoyed it, and I hope there was something new for you, because this talk was mainly from my personal professional experience. That's what I have used, and that's what I used to actually track down, nail down, and fix issues with the program. The problem usually was not in the that I was working with, actually, but I cannot talk for everyone, but for me it was, the problem is usually in a way that something is executed too often, or maybe in proper way. So the problem is usually in the flow. There is a problem also, there might be a problem with the algorithm itself. When you know that the constraint for algorithm is to execute in this amount of time and it doesn't fit, but usually for the whole software, it's usually, the problem is that something takes too long, and then you just take your profiler tool and try to understand where does it take, and you try to optimize the flow, you try to postpone execution as much as possible, you try to minimize contention like locking and for parallel execution, and that already solves a huge amount of bugs, and I mean not bugs, that brings considerable speed up here. So that was my experience, and that's why I wanted to share it with you, because using profiler tools for this is essential. And back a while ago, when at the start of my professional experience, there was only handwritten implementation done, which I showed you at the beginning, and that already brought a significant benefit for nailing down such problems with the code. But there are also very good tools available, and you can just use them, and don't waste your time if that's enough for you. Okay, there is a question regarding source code. I can post it. I will try to post it somewhere, maybe on GitHub, because currently it's only local on my machine. But of course, if you're interested, I will upload it somewhere, and then we'll share it with you.
Okay, it seems like we're done. Maybe someone just have another question or something. And if it's not, thank you guys once more. I wish you a pleasant day. And Christmas time is coming, so take care and join our next webinars.
Thank you for your time, and enjoy your evening actually already.
Thank you a lot.
Thank you. Bye everyone.
Bye. We are waiting for material.
Sure.
You will get everything tomorrow.
Okay.